give me the opportunity to give this talk, this last talk of the day. Now, this talk, as you see from the title, is a parallel from what Sergey introduced and talked about last week. Now, the title is pretty minimal. I reduced it from the original one that was submitted, and it is in the program. However, I'm going to try to say some concepts about that. But first of all, the people. Now, two of the people involved in this project are here. One is David from Boston University, one is Sergey, and two more are now yet still in Korea, Mithun and Yamur, who took part on numerics together with me. Now, as said, Sergey introduced some concepts last week on dynamical glass. Now, here are some of those, some of the most important ones. First of all, integrable system and consequent action angle coordinates. Now, you take an integrable model, you top it up with a perturbation, non-integrable one. The combination of the two, integrable plus perturbation, give you a non-integrable system. And the perturbation considers the action angles and connect them. And therefore, it defines a network of actions. And Sergey introduced that one basic separation of the network of action can be in short and long range. I will come back to that. Now, this is just a reminder of what we heard a week ago. And then there are three items here. Excursions out of equilibrium with their distribution. Finite time average, their distribution, and another time scale called ergodization time, and then last, Lyapunov time. So as you see, there are 6 items in this list. 3 concern the type of model, and 3 more concern time scale. So in some sense, this dynamical glass is a matter of time scale. So comparing time scales in the system. Now, Sergey used as a test bed to present results concerning the dynamical glass, used the system of coupled rotors, namely a one-dimensional chain of neighboring rotors, which are coupled. One rotor is coupled only with the left one, with the right one through Josephson coupling. Now, this is a very important model, in particular for experimental realizations. I will use here another familiar model, which is the Klein-Gordon. Also, Simone spoke about it the previous talk. Now, before to move in, I would like to comment about the former version of the title, which was from intermittent dynamics to dynamical glass. Why? As I started about 2 years ago in this topic, basically I was given a problem of equipartition problem to reconstruct, to reproduce the results by Cohen and Cassetti and others on the FPU chain. So basically to reproduce and potentially improve the results on the equipartition problem. Now, the point was that after the equipartition was reached, what to do with all these data that describe the equilibrium dynamic of the FPU chain. Well, the result of that was that we found a way to, we first of all detected excursions out of equilibrium, and we were able to measure them. And the happy part of that is that that method to detect this excursion were not only good for the FPU, but good also for other models, for instance, the Klein-Gordon. So allow me to recall this. Here is the Hamiltonian, written in the position coordinate Q and momentum coordinate P. So this Hamiltonian was also introduced before, but here we have kinetic energy term, we have quadratic and quartic potential, we have neighboring hopping, and a parameter that controls its strength, which is here called epsilon. Now, here is an example of what I was saying before. Now, here, this is in this x-axis, we have the lattice site n. In time, here in the y-axis, we have time. And then here we take the Hamiltonian and we split it in sum of local energies, here written. We choose periodic boundary conditions, so we actually write precisely the Hamiltonian as sum of these functions j, which now are time-dependent component. And here we look at basically at a time window, where you see that at a certain time, the energy, which is initially, I mean, this is not the initial condition. We arrive here, we see that the energy is pretty much everywhere, but it is at a certain point condensed to one of this function Jn, and it is kept for quite a long time, for time of order 10 to 6, until it is released back. Now, these formations were known before. Here is a small list of papers that are talking about those. One is also a paper by Sergey in 2004, so more than 10 years ago. Another paper is by Stefano and Antonio Politi. And basically what we did in this publication in 2017 and the following one in 2018 is that we have a method to actually detect and estimate their duration. And by doing that, we then can come up with their distribution. So this allowed to have a method to study how these excursions out of equilibrium impact the equilibrium dynamic on a Hamiltonian system, in brackets, close to an integrable limit. Okay, so the focus here is essentially the Klein-Gordon. As we say, we study the time dynamic of these quantities that we decouple the sum as sum of these observables, and here I'm going to speak about mostly two regimes, high energy limit and small coupling. So when the energy density goes towards infinity, or when the coupling is going towards 0. Okay, so here is once again the picture that we have seen before, and here is basically just a very schematic way to show how we detect this time. Here we just take this picture, we fix n to 22, which is this oscillator, and then here we see its time dynamic. This horizontal red dashed line is the value of the energy density, so we actually basically compute the time, the two times where the function J22 is actually equal to the energy density, and then the following one. We take the difference and we can estimate its duration. So it's not really a black magic trick or something. It's just this difference between two consecutive times where your action is actually equal to its energy density. By doing that, we can compute the duration of these events. We can compute also the duration of the smaller one, and then we are able to come up with the distribution of these events. Here is a few examples. Now we see some curves. This is for smaller energy, bit larger, and larger again. And we see that the more we increase the energy, the more this distribution develops fat tails. Now here this dashed line indicates this power law decay with exponent -2, which is a threshold, which indicated that if these times are distributed with this power law tail, then the average of these times is infinite. And that's an interesting fact. However, we don't reach it. We see that the distribution, in particular, let's follow this line, it pretty much resembles for a while until something drops faster. So the distribution drops faster. Therefore, we decided not to compute exponents, but we decided to look at the first moment and the standard deviation. Oh, this thing is not working. The total measurement time was it was around 10 to 10. Yeah. One issue. Now I don't know whether it is visible from over there, but if we look at this curve, actually these are free curves obtained for the same integration time for the same parameter, just increasing the statistics, increasing the system size. And here we show that basically increasing the statistic increase how long the approximation of this distribution, so the better approximation we can obtain, but basically the trend is always the same. So it's not that if we increase the statistics, we actually deform or obtain totally different distribution, we just improve its approximation. Now, in the other plot here, we show the tendency how increasing the energy, basically this is the first moment of the distribution of this distribution time, or this is the standard deviation. So we see that as the energy increases as we are going towards the integrable limit, that is further down at energy h equal infinity. The first moment of this excursion time increase, but pretty slow, and the standard deviation instead increase much faster than the average. So also its ratio, sigma over mu, increases. Now, this is a first observation. Now, we want to see how these times impact the finite time average of these quantities. Here is defined. So we take this function that we have been looking for the excursion times. We define its finite time average for certain initial condition, R0, the time 0. We do it for many times, for many initial conditions at the same energy, and we get a distribution of these finite time averages. So from this distribution, we can compute its average and its variance. Now, ergodicity might imply that the distribution of this finite time average as the averaging time diverges towards infinity, the distribution converges towards a delta function, here centered around the energy density. Therefore, we want to check that. We want to check that this distribution at finite time converges towards a delta function. How do we do that? We want to look how the variance converge to 0. And instead of look at that precisely, we just take the variance, and then we divide it by the average of this distribution squared to make this fluctuation index a dimensionless quantity. Now, we do that, and here are some examples. Now, here from the black curve, this is the lowest energy, then red, bit higher with blue, bit higher with orange, until green, which is the highest, at least that we could have sampled with our simulation. And you see that it appears this some fluctuation, but anyway, pretty much 1/t decay, which is also shown for a bit higher energy, but a bit later. And likewise, for a higher energy, still 1/t decay appears, but a bit later. So you got essentially to wait longer as the energy increase in order that this 1/t decay appears. Now, we call the ergodization time the prefactor of this 1/t decay. We measure this prefactor, and we put it here as function of the energy. So you see, as we get close to the integrable limit, this ergodization time diverges. Now, we want to compare it with the former timescales that we analyzed. So here I introduce, this is the average of the excursion time. This is the standard deviation of the excursion time, and it turns out that these two are connected to the ergodization time by this ratio. So if you take these square divided by this one and introduce a fitting parameter, you see that these two timescales behave similarly, actually very similarly. Now, allow me to complete this picture, which is one of the main messages of my talk. Here I want to introduce the Lyapunov time. Lyapunov time defined as the inverse of the largest Lyapunov exponent. It is here in this black curve. And what I want to point out as the main message of the dynamical glass is that here we are comparing how the ergodization time behave with respect to the Lyapunov time. And you see that one, the ergodization time diverges pretty quickly, and instead the Lyapunov time hangs here. It actually starts to diverge. It actually has to diverge, because as you go towards energy towards infinity, there is integrable, so there are no non-zero Lyapunov exponent. Therefore, this time has to be infinite. The fact is that this divergence is very, very slow, while the ergodization time is fast, a bit fast, at least much faster than the Lyapunov time. And that is basically what we see in the large energy limit. We do the same, an analogous kind of limit. We fix the energy, and we take this number here, epsilon, and we take the limit towards 0. And you see, this is the picture we have seen before. This is the picture for a given energy, namely equal 5, and epsilon that goes toward from 1 to small. And you see essentially a mirror of this picture. So you see that the average of the excursion time diverges. Likewise, the standard deviation of the excursion time diverges much faster than the average of excursion times. Their ratio well match the ergodization time, which is here represented, the ergodization time in orange. The ratio between the square of this divided by this is represented in green, and Lyapunov time hangs here around. And we see a common feature between the two cases. The Lyapunov time is typically smaller than the average excursion time. This is a feature that currently is only a numerical evidence. We don't really have an explanation for that, but at least this is a feature that we see in this type of limit, including the limit observed in the system of Josephson junction. Now, the question is, as I said, we have seen this similar behavior in the system of coupled rotor. Question is this a common feature for any system close to integrable limit? Well, the answer is no, and we found the answer immediately in the Klein-Gordon system. We just have to take another limit. Another limit is when this term here, the quartic term, is absent. Therefore, what the Hamiltonian reduces to, it is a set of harmonic oscillator with conserved quantities, the normal mode energy. So once we introduce this term, and we go towards a small energy limit where the quartic term converges to 0 much faster than all the quadratic ones, now this quartic term becomes a perturbation, but it makes all the normal mode energy fluctuates in time, and we consider those as our observable to detect excursion time and to calculate the distribution of finite time averages. And what we see is here. Okay, let's put the two limits. This is small energy limit, considering as observable the normal mode energies. And here, this is the previous plot, where we go into large energy limit, and we consider the sum of the local energy density, the local energy as observable. Again, quite mirror plot, except one feature, the Lyapunov time. One Lyapunov time here, basically, as we approach large energy limit, it is lower than the average excursion time. Here, instead, it behaves pretty much as the standard deviation of the excursion time. Hence, we conclude these are different limits. These are different cases, better to say. And therefore, this leads me to this slide, which tries to resume all the concepts presented. Here we have a Hamiltonian, which we write as integrable part plus a small perturbation controlled by a strength epsilon. Now, this is what happened in the low energy limit. We have normal mode energies, and this quartic term connects all of them with selection rules, but nevertheless, one normal mode energy is connected to all of the other modes. Therefore, it forms a long-range network. This is what is presented here. So basically, a perturbation couples all the other actions. In this case, this is similar to what happened in rotors. We find that the ergodization time behaves as the Lyapunov time squared. Hence, the two are connected. This is something that does not happen in the short-range network, similarly to what we have seen now, or the rotor cases, where basically one rotor is connected. In the limit, one rotor is connected only on the neighboring one, and that's it. So no connection with all the rest of the chain. And in that case, the Lyapunov time and the ergodization times are disconnected. So there are no relation between the other ones. Now, why we think that this is a separation, at least one of those, is in the nature of this network. So by the short rangeness of this network, one action, for instance, one of these energy densities or one of the rotor momentum, basically is connected only to the neighboring one. So this variable is basically, it can disconnect from all the rest of the system, so the system can fragment. One action performs one of these long excursions. The other actions are free to form groups that they behave chaotically. So the short rangeness of the network allows the system to break apart chaotic spots and regular islands. The regular islands dictate a faster divergence of the excursion time. the chaotic spot gives basically a non-zero large Lyapunov exponent, and therefore the Lyapunov times remains finite and diverges very slowly. This fragmentation instead does not happen in case of long-range network, and therefore no relation. Therefore this relation appears. Now this is only a conjecture, so hence we label this the conjecture, and basically this slide drags me to a conclusion, of my apparently relatively short talk. Now, first of all, open issues. So we have to figure out this conjecture. So is this conjecture correct? Well, for so far, our numerical result and the little amount of analytical result we have essentially is moving us towards this direction, but we have to work out details in order to see whether this is correct or not. And is it this separation in long and short range network all, or are we leaving behind something? Well, since the world of nearly integrable system is so rich, probably we are leaving behind something, but what, we don't know. Now, we have to figure out what is happening in the FPU chain, where we actually everything started, and this is yet an unsolved issue. And then we want to look at discrete time random walks, in particular for improve our numerics. And then this is a very long-term goal, which most probably will not even take myself, which is everything we are talking about now, our classical system. Is there any relation with quantum system, in particular with MBL and non-ergodic metallic phase, question mark. And with that, I thank you.